Thank you very much for your introduction. It's a pleasure to be here. And my name is Dirk Beyer from LMU Munich. And I would like to give a talk about find, use, and conserve tools for formal methods. And what does this have to do with Andreas? So first of all, congratulations, Andreas, not only to the birthday, but also to the many achievements in research. And since Tom has talked already about the theoretical results, I would focus on tools here. So you and your research group have developed a lot of tools, and they had a lot of impact. Two prestigious examples are the family of the family of tools for software verification, and as SMT Interpol, the SMT solver. Both have had enormous influence on the research community and have taught us how to do things. And by the way, Ultimate Automizer, for those who don't know, is the world champion of software verification, actually the 2 times in a row even. And so these tools... It will be from now on always? Okay. We will try hard to change this. But it's hard to succeed with this goal. So there are excellent features and performance, and there are lots of medals also in the competitions. And the open problem is there could be a day when Andreas doesn't come to university anymore and enjoys wine and life and food and whatever, his wife and Elsa's. And then what happens to these brilliant tools? And this is what my talk is about. So my humble contribution to the work of Andreas will be to conserve tools, or to show a method how to conserve tools so that the tools survive the office or the times when Andreas is in office. So our vision that we have is, well, all the tools in formal methods should work together to solve hard verification problems and make our life safer and more secure, as Tom pointed out earlier. Model checkers and theorem provers should be integrated into software development process as seamless as unit testing today. Model checkers, theorem provers, SMT solvers, and testers should use common interfaces for interaction and composition. So this vision is hard to achieve. It could be a long-term challenge, but I want to show a few little steps towards this vision. So first of all, let's talk about the find component of it. So, which tools for software verification exist? I don't want to ask you for names, and you know one already, Ultimate Automizer. So let me ask a simpler question. What do you think, how many tools for software verification for the C language are available today? Who thinks 10? Who thinks up to 20? 23.
65. I go higher. I want 71.
Okay. How do you know, where do you get this number from? Is it a guess or did you look up?
I can't say it in what I don't.
So the number of tools for verifying C programs that participated in the last competition were 59. 59, yeah. So counting also those that are meant for validation and can generate tests, we would have 91. So it's amazingly large number, and some of you were smiling when Ranjit said 65. So it's hard to know, right? So we need to do something about this. So this is one thing that we have to improve. So what can we do to support people finding our tools? for test case generation or for SMT solving or for hardware verification and so on. And the next, once we have done this, that people are able to find our tools, we need to make sure they get reused. This is a next question. So out of these 59 or 65 tools, who would expect that you are able to get the tool running within 10 minutes? Okay. Who would say I am able to get the tool running within half an hour? Okay, so this is really embarrassing. And this shows us the state of the art, right? So we have the tools, we can maybe find them, but we cannot use them, right? So why do we have them? This is the next thing. So we have to do something to to make it possible to easily get the executables, to find documentation, to get them running. And then the next question is, even if you would have the tool and you would know how to run them, then you would probably have the wrong machine, not installed with the good operating system and with the packages you need. And this is basically the third big thing to conserve. So we have to specify what operating system does it need, what libraries does it need, what's the environment in which it can run. And this is what I would like to work on. And the requirements for a solution would be, okay, it must support documentation and reuse. It must be easy to query and generate a knowledge base out of it, because we want to find. It must be long-term available, and it must also ensure long-term availability of the tools, long-term availability of the tools. It must come with tool support, and the approach must be compatible with the competitions, because the competitions are really important for our research area, because it keeps us, it keeps the tools up and running, it keeps them maintained, and it gives us yearly evaluations, comparative evaluations of the tools. So we must support competitions also. So the solution, the little step forward that I want to propose is a central repository that gives information about the tools, where to find the tool, and in particular make it identifiable via a DOI, just like other literature, so software is literature in a sense. What license does it have? Who is the contact about it? What's the project webpage? Where can I find more information? What options do I need to use in order to get the tool started as the developers would recommend to me? What are the requirements? Like what's a Docker container or a virtual machine to start it? What are the limits to start with, and so on? And this must be done in such a way that it is maintained by the yearly competitions that happen in the field. So this is the plan, and next I will show you how this looks like. So we are talking about little YAML files that contain some information and which can be then used to query the information and do everything else. So I want to show you for the as an example one of Andreas's tools, Ultimate Automizer. So and this is how the information looks. Why am I showing you these technical details? Well, just to show you that it is simple, right? I want to make a case of simplicity here. So first we say, what's the name of it? What input languages does it support? Where do I find more information? The project URL. Where do I find the code for it? What is the license? So what can I do with the tool? This is very important. Can I even download it? Can I even execute it? How can I extract information like command lines and interpret the outputs of the tool? What's the version of this file, right? And who is the maintainer of this whole entry? And this entry goes on with, for example, specifying contacts. So if I have questions about the tool, whom can I contact? So here's a list of maintainers. you know, with, of course, with an ID, with name, institutions, country, and where to find more information about them. The versions. So how do I specify a version of a tool? So I say, for example, this version has the name as vcom24. This was the version that was submitted to a competition. The version of the tool has a DOI. So this is the identifier which I can use to download the exact version that was used in the competition. And this is the options that I need in addition to giving the specification and the program as input. And these are the required packages that the tool needs. And here is a container that I can use to get the tool running. And if I don't want to bother with installing packages, I can, well, I shortened this a little bit. There's a full container image that everybody can use. If one is interested in the participation in competitions of the tool, and this is also supporting the organization of the competitions. So, for example, here we say that, okay, Ultimate Automizer participated in the competition as vcom24 in the track verification with the tool version. You know, this is a reference to the particular version that was used, and this is the jury member who was responsible for taking care of getting this tool into the competition. And next, last, there is a section where you can declare what techniques it is using and supporting. Of course, the list for Ultimate Automizer is very long. It would fill the slide alone, but I had to abbreviate. And you can also give literature about the tool. For example, here, I think the most cited Ultimate Automizer paper is thermal checking for people who love automata. And there's also competition contributions where the new advancements of Ultimate Automizer is described. Okay, so this basically is such a file. And what can we do with this file? Actually, this repository should fulfill the so-called FAIR principles. What does FAIR mean? Well, the stuff must be findable, accessible, interoperable, and reusable. Well, how is it findable? Well, there's an overview on the internet. So all the information is available on the internet, and we can generate a knowledge base. I will maybe show you later if you have time. It's accessible because all the data are open. It's retrievable via the Git, or via the GitLab API, and the format is YAML, so it's very easy to query. It's interoperable because there's a schema for it, so everybody can look up what's the syntax of it. And yeah, for the archives, we use DOIs. So with the DOIs, there's more information about the entries in Crossref or in DataSite or whatever they are called. And the researchers are identified with ORCID, and the researchers can give as much information about themselves as they wish there. And it's reusable because all the data are CC BY, and also each tool comes with the license telling the people what we can do with the tool. And of course, also the format for the tool archive is standardized. Okay, so now what about the environment? I said one of the requirements is we need tool support. So the data alone is only half of the story. We need tool support for it. So now if we have all these computers and we want to make sure we can run on them. And there's a tool that is called FMVec. The meaning of the name is probably only understandable for Germans who know VEC glasses to conserve fruits or vegetables. Also, you have these glasses, and they are called. There's a company called VEC in Germany. So this is formal methods VEC, and it is made to run the tools. For example, Andreas's tools forever. Hopefully. So what do you do is you call FM, this is a command line. So you say fmvec and then run. It's similar to, who knows, Docker, right? Run is the command for it. But here it actually downloads and installs and runs the tool in the specified Docker container. So this fmvec looks up in the data that I showed before. What's the Docker container that this tool needs? and where to get the tool. So it looks up the DOI, gets the tool downloaded from Zenodo, and executes it, right? And here, basically, it says, okay, which tool and which version of the tool I need. And this is, well, this is more of the command line. So what do I... What do I do? Uh-huh. Ah, yeah. Interesting. Okay, so there's also the property to check, you know, we want to check, for example, the unreached call specification, and there's a file given. So you don't need any knowledge about the command line interface, right? So when I ask you again to execute, you don't need to look up, you know, what command lines do I need to use. And the tool runs in a container. So even if you don't have Linux, if you have only Windows, it runs. Yes, Tom?
So, but that unreached call, is that something that's common to all the
So yes, so basically you can give here a file with an ending PRP, and this is a syntax that is defined in the competition on software verification. This is an attempt to specify, to have a common language to specify what we want to check. And there are several, like 5 or so specifications that are very common, like reachability of some function call, which is this. Like there's a call function specified that must not be called. There is memory safety, there is termination, and there are some other, like data races and so on. So these are referred to with names, and this is just a shortcut, basically. The standard way would be to give a file there, and the file contains the specification in a format that the tool understands, right? So this is also an achievement of the competition. So we have 60 tools that understand the same language for the specification. So you need to learn only one language and then it works. Whereas in the community of deductive software verification, you have to learn the different languages for writing down invariants and requires and ensures. Right? There is no standard for that. Okay, so how does the tool work? So there is this FMVec also handles caching. It starts the container and it takes as input some user-defined specifications and the YAML file that I explained before, and it will, you know, support commands like fmvec run, or if you want to give own command lines for the tool, you can also open the shell with the tool installed in the Docker image that the tool developers want you to use. And here is the 3 main modes that the tool has. So this is the main one: download and execute the tool in the container. No knowledge of the tool is needed. Here you run with manual mode, M for manual. So it also downloads and executes the tool in a container, but you can give more command lines that are native to the tool. And the shell would spin up a shell for getting interactive. You can also, use a tool as a web service. I know that for Ultimate Automizer this is superfluous because Ultimate Automizer has already a web service that users can use, which is very important for people to try out without bothering to install, and it's also important for teaching. For, you know, if you're in a classroom and you want to show how things work, it's easy to have a web service for it. So Ultimate Automizer has an own one, and this is one that is transparent for the tools, so it works with any of the tools that are supported in this repository. And it does not only have a website to run the tool, but it also supports on command line via web API using a REST interface. So the user here sends a request with the information about the tool and the verification task, and the Conserve team service, that's the name of it, prepares the environment, like downloads the image, downloads the tool, installs the tool in the image and runs it, right? Invoke and bundle the results and sends it back, and Conserve team takes care of downloading the tool and execute the tool, and the tool output and the generated files are given back to the user as the output. Right, so this basically gives a way to execute tools on a remote computer that is maintained by somebody else. There was also an effort by Microsoft, the Rise for Fun, right? And this was a very nice tool, and many people have used it, but it was discontinued. So we need something as a replacement, and we tried. Okay, so the conclusion. So FM Tools, this repository collects and stores the essential information to do a certain number of things, like run a tool as a web service, run a tool in a conserved environment, generate a knowledge base about the formal method tools, and organize competition participants. And now I will show you this generated website where tools can be found. But how to get rid of? I don't have. So as I explained before, there are a bunch of YAML files with information. They are easy to retrieve and to query information, but we can also make this more user-friendly and to support the findability aspect of it. So here is a list of two. Oh, I'm talking about something that you cannot see. Settings. No, apply, keep. No, you see the same as I do. So this is a web page generated from the information, and now you can see what tools are around. So these are the 91 tools of it. Unfortunately, Ultimate Automizer has a disadvantage if it is alphabetically sorted. So you go here, and here you see the information that you need to know, if you want to see, is Ultimate Automizer something for me? So you look at, okay, what does it support? It supports algorithm selection, automata-based analysis. It's good if your program uses bit operations. It's using CIGAR. It's using predicate abstraction, ranking functions are supported, and so on. And what is it based on? So it's based on good. It's based on good stuff, high quality, components, as you can see. So it's expected to run stably. Here is the literature if you want to read about it, and here is even presentations. If you want to learn something about it, you can get a quick overview of the tool. And if you want to look up what it has competed in terms of competitions. Of course, this is still incomplete here. It has only the last year and not all the last 10 years. And yeah, this concludes. Thank you very much for your attention.
Any questions or comments for Dirk?
You said you want to preserve the tools, but still I see maintenance persons are still behind it. So if these persons sort of turn away from the tool, what happens then?
Yeah, so yes, so we have. So you are referring to this part of the information, and so these are the maintenance of the tool. If they become inactive, that's of course a problem because we don't get the good advancements of it. But here we know that the tool in this version is archived at this DOI, and this is a Zenodo DOI. Zenodo is government funded by the EU, so it's a CERN feature at the CERN project, and we hope that it does not disappear. So the tool will be what we call forever available on this in this digital library Zenodo. So we can download it from there, and the Docker containers, they will also be available. Here I use IDs that are currently available and make it convenient. And now you might argue Docker also at some point might discontinue, but we will also store these Docker images on Zenodo so that they are also retrievable in the future. Ranjit had a question?
Is this on? Okay. So my question is, if you go back to the beginning of your talk, your thing was how do you think you can run it in 10 minutes, 30 minutes? That was a question you asked, right?
Yes.
Now, one of the dimensions, sorry?
Install.
Correct. Install and then presumably run as well. Now, one of the dimensions that I think you have not considered is you're assuming that, so it means you're focused on C over here, right? But if you sort of generalize, but it applies to C as well, is C is not a static thing anymore. And so when you write these tools, you are targeting it towards, some version of C that exists right now. And 10 years later, we're in this regime where Andreas is enjoying, how did you say, wine and so on, right? And is not coming into the office. So C sort of evolves. And now if newer C programs may simply not run on your tool. So what thoughts do you have on that? So all of this is, you're making it super easy so that the same set of benchmarks will continue to run regardless of where Andreas shows up, right? Because you've got this nice sort of Docker freezing and so on and so forth. But the language itself is changing where, people are going to be adding little pragmas and this and that and little syntactic constructs. And so the tool itself has to change. I mean, do you have any thoughts over there, or is that a kind of lost cause?
That is a very nice and interesting question, and I could talk about it for a very long time. So the short answer would be, I don't have a good answer. So this is an effort to conserve what we have. So we cannot predict the future. So we can only say, okay, what is available today? We can conserve and we can make it easy to use. And if the maintainers of a tool decide to support the most recent features, then this machinery also supports it. On the other hand, there are, it's not connected to this topic, but there is a research, a research group or a research area starting about transformation, where you might have heard about this MOXIE intermediate language. And there are actually also existing intermediate languages for programs. So if we have a network of transformations that transform programs from one programming language into another, then we could also overcome the problem that if we have a new feature and we want to use an old tool, we could transform the program into a C program in the old style. in the old language, and then we could use the old tools. We have an interesting movement going on where we try to bridge the gap between hardware verification and software verification. So we are able nowadays to use hardware model checkers like ABC and AVR to verify C programs by converting C programs to hardware circuit languages. And also the other way, we are using software verifiers to verify hardware circuits like in B2 or in Eiger. And this makes it, this makes me hope that this is possible, that we can transform the new features to an old language, if we even can transform between software and hardware, right? And yeah, let me stop here with.
So I'm very interested in general, and goes back to SLAM, in sort of learning API specifications. So currently, I'm looking at it from a black box perspective in testing. But I wonder with these tools, I mean, they're learning invariants, they're learning something about the code, and at a certain level of abstraction, say the interface abstraction, you could persist them, but you could also compare them. You could say, how do different tools represent, you know, precondition, postcondition for a C function call, and then you could actually like take those formulas and maybe compare their strength in some logic relative to one another. So I'm curious to what extent, and this is related to deductive verification and the problem you previously stated about, you know, different languages. But I'm curious to what extent you've looked at, or the competition has looked at ways to surface, you know, intermediate, more knowledge. I mean, these automated engines are computing something, but it's not really being exposed, is it? And if so, why not? And do you have a path towards that?
I'm not sure if I completely understand. I think one of the answers is that the automated software verification tools, they are exporting witnesses, verification witnesses, and they contain invariants, for example.
Okay.
So about like a part of your question was, do they expose their results? Do they expose their what they found out about, right?
Right.
And current state of the art is just invariants, not requires ensures.
I see.
But the all these C verifiers that are supported here, they are exporting a verification witness that can be either a correctness witness, then it contains the invariants that are needed at loop heads to prove correctness.
I see.
And then there are also works on taking these witnesses and transform them to annotations. Like you take a C program and a witness, and then you compile that to an annotated C program. For example, in ACSL notation. Because you only need to peel out the invariant from the witness and put it in as annotation.
So you have examples where like somebody creates the witness and another tool consumes it?
Yes.
And checks it? Oh, okay,
there are
great.
papers about this, yes.
I'm behind the times here. Yeah, thanks.
So let's thank Dirk again.
Thank you.